Hello, everyone. We're Group 7, and we're designing a 3D printer for bone scaffolding manufacturing. My name is Colton.
I'm Amy.
I'm Brittany.
And I'm Ryan.
So every year, there are around 500,000 patients that require some sort of bone repair or restoration in the United States, leading to an annual cost of over $2.5 billion. Added onto this, there is a prediction to have doubled amount near the year 2020 due to the baby boomer generation coming to a median age. This is added on to those who have serious bone fractures and need bone regeneration, such as soldiers. When the patient has a fracture that is unable to heal itself, they will go through the procedure of having a bone graft, which requires a section of the patient's bone to be removed and then have a 3D bone scaffold put in. Modern bone scaffolds are limited to current technology and are limited to the amount of acquired supplies. Another pressing issue is the porosity of the scaffold, as well as the cellular geometrical formation has yet to be greater than 50%. So as a theoretical solution, it is important to have a printer that can print both the cells and the polymers synchronously to potentially solve this issue, or have hospitals and research facilities add on to this baseline idea.
Our approach is a specific solution to combine bioprinters for scaffold materials and bioprinters for cells to incorporate the cells layer by layer as the scaffold is being printed. This solves the problem of cells not being uniformly distributed in the scaffold, but also allows for adductive and mechanically strong properties. Our plan is to have two nozzles, one for the scaffold material and one for the cells. The nozzles would be able to be changed out to include other materials or for other sized nozzles, which can have a range from 30 micrometers to 130 micrometers. The cell nozzle will act like a counter pipette to dump cells into the pores of the scaffold along with growth factors and nutrients. The thermoplastic polymer nozzle will heat up to extrude the polymer and be cooled before the cells are put into the pores. We'll use CAD to plan out the structure of the printer and use manufacturing machining to make the actual printer.
Benefits and cost analysis show the value of the solution would be that the patients will not need another graft in the near future and will increase the healing. The increased induction of the material due to patient cell infused 3D printing will expedite this process and ensure that the cells will bind with the patient. The increased function of the dynamic nozzle will reduce the need for changing the nozzle, which increases the time it takes to create the final product. The costs associated with making this product are estimated at roughly $150,000 based on present technologies. The cost of creating the bioink involves culturing the patient's cells, then placing them in an incubator, which slowly mixes the cells into an ink. Costs of PLA spools are roughly $50 for a spool and can be accessed through multiple vendors.
In the current market, there are a variety of approaches to 3D printing bone scaffolds. Commonly used materials are bioceramics, hydrogels, polymers, and synthetic or natural tissues. There are limited designs and materials that are inductive when introduced to the body. Our design would achieve this since there are cells and other biomaterials injected while the scaffold is being printed. There's also no 3D printer that is commercially available that can switch between printing a polymer to injecting bioink. The nozzle size for printer could also be changed during the operation to have varying thicknesses and roughness of the scaffold. The change in nozzle diameter is also essential for a bioprinter to prevent killing any cells while it's being extruded. If our design was not implemented, patients would have to resort to using traditionally printed scaffolds. For example, polyester scaffolds struggle with evenly distributing biomolecules and cells within the scaffold. This is because there is not enough micropores in the scaffold to absorb these materials. This kind of design becomes more mechanically weak in compression as it becomes more porous. Our device would allow even distribution of biomaterials since it will be layered on during printing. There are also less post-printing steps when creating our bone scaffold since the biomaterials are already in the design. Thank you so much today.